Okay, so TempleOS uses LZW compression, not encryption. On the CD that it's distributed on, the ISO, there's a Linux directory with a file called TOSC, and this is a standard C program for uncompressing that you can run from Linux. So in the boot directory, there's the source code for the bootloaders. MHD is the master hard disk bootloader. When you do a boot, this is the TempleOS bootloader. You can boot the C drive or the D drive, or whatever was there before you installed. So if you have Windows and then you install this on top, then it will probably boot Windows if you press 0. Or if you have Grub and then you install this on top, it will probably boot Grub, because it takes the block that was there and it stores it. So the C drive, it goes from block 3F to 80,000 or 800,000. Anyway, there's a gap when you partition at the beginning, and most bootloaders use the gap, but I do not use the gap. I only use block 0. So where do I put the rest of it if I'm not using the gap? Well, there's a directory called 000 boot, and this is where the rest of the bootloader is stored, along with the old boot record, so that it can do a boot the old record. Now, all that UEFI needs to do is read the first block and jump to it. Everything else we're going to order them to get rid of. That's all fucking bullshit. Okay, all it needs to do, load the first block, jump to it, and I guess provide a way to read other blocks. The whole EFI is a crock of shit. All it needs to do, load the first block of the drive, jump to it. Okay. Okay, so we're going to look at my bootloaders. These are old BIOS bootloaders, not UEFI. I am not going to do UEFI. So my BIOS bootloaders for the hard disk, all of my bootloaders relocate themselves up into high memory and then load the code at 7C00. Why? I don't know. I want my bootloader in a known location, so I relocate it up to the top of memory for the 640. Anyway, so it copies itself up to 9CC0, and then it loads one block at a time using interrupt 13, number 42. This is the one for large hard disks. So pretty much any hard disk over 130 gig, which is everything. There haven't been small drives in 12, 15 years. Anyway, so this uses the large hard disk bootloader. The large hard disk block read. It loads one block at a time. Now, it has a hard-coded disk block and count, hard-coded. So, a lot of people just, I don't know why they're so stupid. So, when you make an operating system, this is how it's supposed to work, okay? When you go to the website, operating systems are shipped on ISO files, so you download the ISO file, and then you go into VMware or whatever, typical, you point the CD-ROM to the ISO file, other 64-bit, 8 gig for disk, customized hardware. I'm going to give it 40 gig. I'm going to give it 16 processors. We don't have a network. We don't have a sound card. Okay, the way an operating system is supposed to work is you boot the ISO, and then the operating system has an install. Okay, yes, we want to install on the hard disk. Are we in VMware? Yes. Press a key. Yes. Okay, the people at OS Dev think that the operating system that you should compile it. No. They want to compile it and boot it themselves. My compiler is the only compiler that can compile it, and my compiler only exists in TempleOS. So you have to go through the door before you can do anything. So to use my compiler, you have to be inside of TempleOS. And do you want to reboot? Yes. When I run my install script, guess what? It knows, it recompiles the kernel. So kernel.bin is created. It happens to recompile when you reinstall. Now if we do a directory star, guess what? Here is the cluster number of the kernel.bin, and all my files are stored contiguously. Okay, so guess what? It puts the cluster number of kernel.bin into, okay, into the bootloader. It puts the cluster number of kernel.bin when it installs into the bootloader. Your kernel obviously has to navigate the file system, right? Your kernel has to know the file system. Why did you bother to make the file system in the bootloader? If you have it in the kernel, just use the kernel. My dog wants in. Say hi, come here. Come here, say hi. I want minimum lines of code, and therefore I do not want to navigate the file system in my bootloader. My bootloader has an absolute block address. In other words, if you move the kernel, it won't boot. Okay, so you have to reinstall the bootloader or repatch the bootloader when you modify the kernel. That's not a problem because this routine will recompile everything. There's only two modules, kernel and compiler, and then it patches the bootloader. See, here's where it patches and then it writes a block to the boot sector. This really confuses the hell out of people. I get tired of explaining this over and over and over. The same fucking... I also have to explain that it's compression and not encryption. It's compression. Okay, so my kernel is a flat binary. It starts here in 16-bit mode. It calls some BIOS to change to VGA 640 by 480. A lot of people think that this is text mode, but this is not text mode. So changes to 640 by 480, and it gets the memory map from the BIOS, sets up the global descriptor table. All of this code is position independent. So basically I figure out where I am. I figure out where I am by calling here and popping the address and dealing with the code segment. This is how you make position independent code. You call to get the IP and you shift over the CS. Now you have position independent code, or you have a pointer, and then you can put it into the GDT so that your GDT, so this we could relocate kernel.bin when we boot. The bootloader could load it into a new location. It switches to 32-bit mode. Then it patches all the absolute addresses. My compiler makes binary files that have a list. It's self-modifying code. It patches all the absolute addresses and sets up the it has to set up the GDT. It has to set up the page tables. So I used to have just a simple identity map, but then I made an alias that's uncached for the first 4 gig, and I use 1 gig page tables if possible. Otherwise, I use 2 meg. What else do you want to see? I get tired of explaining the same things over and over. Hello? This is Terry A. Davis. Oh, okay. Excuse me? What? Uh, I wrote everything from scratch. It's not Flash. It's a 3D projection that I wrote it all from scratch. What do you want to know? I wrote everything from scratch. What part of from scratch do you not understand? No, I wrote everything from scratch, all the way down to the bits. Okay, I wrote the fucking compiler, I wrote the fucking graphic library, I wrote everything. It doesn't use any other formats. It uses my own formats. It doesn't do Flash. It doesn't do ELF. It doesn't do anybody else's formats. I wrote everything from scratch. Yeah, okay. Okay, bye. This is, okay, let's talk about that. So, he wants to see my 3D mesh. So, first of all, if you say Control R, make Sprite, make 3D mesh. Now we can say, let's do a prism, 25 thickness. Okay, so what we just made is a 3D prism. Let's go ahead and change color to green. And let's go ahead and let's make a prism. Okay, now we exit. So what we just did is we just made a bunch of triangles that have vertexes and colors. Okay, there are triangles that are made of vertexes and colors, and we can put the triangle. We can make a file, a source code. This is source code. We can put the. I wrote my own compiler. I wrote my own graphics library. I wrote everything from scratch. So we can put this into the source code, and we can say Sprite Control R pointer. Okay, so we're gonna output a sprite to the command line, and it's there. We output a sprite to the command line. We output 4 sprites to the command line. Okay, so I wrote everything from scratch. If you want to see what the sprites look like, you can edit them as text. They're not stored as text. They're not stored as text. They're stored as binary. But if you want to edit as text, you go to Sprite, edit as text. It's vertexes and triangles. Vertexes and triangles. Now if you dump this file, dump test.cpp.z, it's got binary graphics at the bottom and text at the top. Okay, so the sprites, this is not an archive. What it is it's a file. You can kind of think of it like PDF. It's got binary graphics and ASCII text. they're actually stored compressed. The dump uncompresses. But anyway, so you might wonder, why does it rotate? Well, if we go to the document editor, obviously we have an editor, the editor for our document. Let's look for Sprite. Sprite mask. There's where it outputs the Sprite. And what does it do? It takes the current time and does a rotation. We don't want the angles synchronized, so it rotates in 3 angles at slightly different amounts. So that's why you get the standard rotation like this. Anyway, so we can look at the draw triangle. Why don't we make draw triangle? There's a lot of people. This is going to blow your mind. Okay. Let's blow your mind. Okay, so first of all, while not let's see what this does. Hello? Yeah. Are you using TempleOS? Well, that's your problem. Okay, so somebody thinks that it's a GIF. So x1 equals I'm the best programmer on earth. I was given divine intellect, and TempleOS is God's official third temple. The Bible is divine intellect. TempleOS is divine intellect. Not animated GIFs. It's I just showed you the document editor where it rotates the sprites. Okay, so what are we doing here? We are getting the position of the mouse. We're waiting for the left button. We're recording the position X1, Y1. We're drawing a circle, radius 10. We're waiting for the mouse to go up. So I'm going to do 3 clicks. 1, 2, 3. Okay, now we're done. Okay, so, and we want to say, press a key, DC fill. Okay, so press a key. Okay. Click, click, click. Press a key. That looks like shit. Okay, we're gonna do win max, win border. This maximizes the window. Settings, push. Settings, pop. Okay. So now we go click, click, click. That looks like shit. Okay, we say dock clear. Press a key. Okay. Now we're good. So we clicked 3 times, and now we're going to fill a triangle. Okay, so I64X, comma, we want let's do this for children. F64 slope. Okay. So X comma Y. So let's say slope equals, now let's make it so that it's always here, here, here. So we want our triangles are always going to look like this, 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 okay? So let's do slope. Slope is equal to rise over run. Do you remember that? So the rise is Y. Is that what we want? Actually, we don't want that. We want the we're going to step 1 row at a time and draw horizontal lines. And slowly, this is going to be the inverse slope. Inverse slope. Slope. Inverse slope is equal to x2 minus x1 divided by y2 minus y1 for y equals y1, y less or equal y2, y plus plus. Let's just draw a line, GR line. Okay, you want to do X as well? We might as well. For X equals, oh, we have to okay, comma, XX1, XX2. Okay, so XX1 equals X1. No, let's do left and right. That's right. X left. X right. X left equals X1. X right equals X2. X1. Actually, as a matter of fact, inverse slope left, inverse slope right, inverse slope left, inverse slope right. Oh, you know, I got this backward. We're doing 1, 2, 3. So as a matter of fact, the left is 3, 3. Okay, so now we say for x equals x left, x less or equal to x right, x plus plus. GR plot, comma, x comma y. Okay, and then what do? We say x left plus equals inverse slope left and we say x right plus equals inverse slope right. Let's see if it works. Okay, we're going to draw 1, 2, 3. Oh, what the hell did I do? Okay. X left is x1. Let's just do this. That looks correct. Oh, there, it worked. I wonder if what the hell? Maybe I didn't do my triangle correctly. Okay, that's, okay. I must not have done my triangle correctly. Okay, so now we have to do the bottom half. That's the top part of the triangle. Now we're going to do the bottom part. So we leave left and right the same. As a matter of fact, the left is still the same. The left is still the same, but the right is now x3 minus x2, y3 minus y2. Is that all we have to do? Click, click, click. Shit. What the truck? What is your malfunction? I'm really claustrophobic. Okay. Y2 to Y3. Click, click, click. This is kind of embarrassing, isn't it? What do we got? We got click, click. That's not going correctly. X left is inverse slope left is 0. What? Oh. Weird. I have no idea why. 0. Oh, it's integer. Okay. 2F64. You might not know what that is. Okay. So this is gonna work. It didn't work. I hate when that happens. Okay, that's because, let's change all of these to integers. This, folks. Okay. Normally I do these with 32-bit. Yeah, that's better. Okay. I'll tell you how I normally do it. Oh, fuck it. Never mind. Normally I do fixed point integer math. There. So we made a filled triangle. Now, how do we, somebody thought it was an animated GIF. No, I'm not I can fucking write a graphics routine, okay? I'm not okay? I can write. You want to do a 3D projection? Is that what makes you confused? It's just a matrix multiply. Fucking niggers. You're using a GIF. I am not using a fucking GIF. I'm not a fucking nigger. Okay, where were we? I don't know. So, some doesn't understand why I was going to do integer math. Okay. Why was I going to do integer math? Well, let's compare integer math to float math, okay? We are going to compare integer math to float math. Integer math compared to floating point math. we are going to compare integer math to float math. Float. Okay, so this is float. Now let's do it as fixed point instead of float point. So we call this F64. We call this I64. Okay, so now we are going to do integer math. You might ask, how can you do that as integer? Well, it's 64-bit. Am I right? Guess what? We use 32 bits on one side of the decimal point and 32 bits on the other side of the decimal point. And so we take 32 bits on one side of the decimal point and 32 bits on the other side of the decimal point. Okay, so the left and the right we're going to do a little bit better. Oh, got it first time. Okay. Okay, so I don't want this done over and over. You know what? The plot probably takes 60%, I'm guessing. So we're not going to see a big difference. But it should be noticeable. Okay, well, let's just leave it like that. Okay, so let's use times. F64, T0, TF. I T0 equals 4I equals 0, I less than 1, 10,000. TF equals T sub S. Float time took 1.6 seconds. Integer time took 1.3 seconds. That's why we use integer. Okay? Let's try it again. Now it's good to do these. The one that goes first might be at a disadvantage. Okay, so cache, it's not an issue on this example, but whenever I do a timing, I always pay attention to cache, because the first time you run a test, it might be in cache, or not in cache. Okay, so that is why we do fixed point. Okay, you'll notice there's a slight difference in anyway, that there's error. Okay, so some wise ass was making fun of integers. It's because he's an